So I've been teaching math and statistics at the college level for like almost 15 years now. So it wasn't really surprising when a buddy's son was taking the AP statistics test that they reached out for a little bit of help. And so we did some review together and it ended up being pretty fun. So that inspired me to make some videos on the AP statistics test. The test that I'm going to review is the 2012 practice test. I chose that one because I found it directly off the AP statistics website. But it's worth pointing out, as you see in front of you, that there's going to be some revisions made to this test. As early as 2027, they're going to change some stuff in here. However, I read through this stuff and none of it is super major. So I still think it makes sense to review the 2012 test, even if you're taking a test after these revisions go into play. What I'll do as I'm making these videos is just comment anytime we come across a topic that might be different in the revised version of the exam. So these videos should work for people taking the exam prior to or after the 2027 changes. Anyways, question 1. This is a question that ideally you'd be able to look at and just kind of tell what the answer is. This is a timed test and time absolutely will come into play. So when there's questions like this one that you can answer really quickly, it's pretty important that you do so. What we're being asked in this question is just which of these data sets has the greatest standard deviation. They're trying to test whether the test taker has kind of an intuitive idea of what standard deviation means. If you're able to look at this, spend, 30 seconds or so analyzing the different dot plots that represent the different data sets and conclude that set B has the greatest standard deviation, that's great. That ends up being the right answer. And that would have been sufficient to answer this specific question. However, the goal with these videos isn't to necessarily help you answer the questions that were asked in the past. It's to help you prepare for questions that will be asked in the future. And so even if you were able to get this right, if you can't kind of argue why this is the right answer, I think it's worth spending a little bit more time on this question to review why exactly this has the greatest standard deviation. So there's lots of arguments for why this has the greatest standard deviation. The way I thought about it is that the standard deviation is just a measure of dispersion, which is a fancy word for spread. But if you stop your kind of informal definition here, you might mistakenly think that A has the greatest standard deviation, as these observations are kind of the most spread out from each other, loosely speaking. Whereas down in B, we're kind of clustered in these two separate groups. So rather than think about the standard deviation as just a measure of dispersion, think about it as a measure of dispersion from the mean. What's nice about this specific problem is all 5 of these data sets have some nice symmetry going on. They don't explicitly tell us the values of the data points, but the symmetry allows us to figure out what the mean is. I can draw it by putting a line right around there, I guess. Sure, that's good enough. First, convince yourself that in each data set, the points are equally spread out to the left and right of this line. And then convince yourself that that means that the mean is exactly at this line. It appears to be around 5. And with that in mind, maybe you can convince yourself that the dots in data set B are furthest from this line. And then maybe you're like, wait, that's all it is? I just need to add up the distance of each of the observations from this line? Well, no, not quite. Really what you need to add up is the square of the distances of each observation from this line. So this observation right here is really close to this line. What's that distance? I don't know, like 0.3 or something. It's not that 0.3 I'd be concerned with. It's the square of that 0.3. 0.3 times 0.3 is 0.09. The contribution of this observation right here, if this observation is at 4.7, which is about what it appears to be, to the standard deviation would be 0.09. The difference in these two values, 0.3 squared. So with that in mind, maybe you can convince yourself that the sum of the squares of the distances of each observation to the mean is greater in data set B than in any of the other data sets. Right? If you compare B and D, for example, these 4 observations contribute the same amount to the standard deviation that these 4 observations do. And similarly, these 4 observations contribute the exact same amount to the standard deviation that these 4 observations do, because the squares of their distances will be the same. But these 2 observations, because they're further from the mean than these 2 observations are, will contribute a greater amount to the standard deviation because the square of that larger number will be greater than the square of the smaller number. If you really wanted to prove, which is not necessary for the test, but may be good for your understanding for future problems, that the standard deviation in B is greater than the standard deviation of A, what you could do is kind of line up observations. These guys contribute the same amount to the standard deviation, but this contributes more than this contributes more than this contributes more than this, and this contributes more than this. Same logic over on this side where these contribute the same amount, but this one contributes more than this one more than this one, this more than this one, and this more than this one. That's probably enough with this problem, and I probably could call the video good here, but there's one more connection that I want to make before I end it. And it goes back to the formulas that they provide you with for this test. There's a bunch of formulas, and in some video I'm going to go through and talk about each of these different formulas so you know where they apply and where you'll use them. But the only one that's relevant for this problem is this, the standard deviation formula. To really be an expert on this problem, it'd be nice if you could tie together this kind of intuitive feel that I talked about here with this formula that we have for the standard deviation. A little hint that might be useful is often it's easier to consider the variance than the standard deviation. All the variance is the square of the standard deviation. So all that does to our formula is cancel out the square root. The important thing to realize is that if a data set has a greater variance than another data set, then that data set will automatically have a greater standard deviation than that other data set, because the square root of a larger number is bigger than the square root of a smaller number. With that in mind, let's make the connection between this variance formula and the argument that I made earlier, claiming that data set B had the largest standard deviation. The first thing to note is that in each of these data sets, there's exactly 10 observations. That is, n equals 10 in each of the 5 different cases. By the way, there'll only be 4 cases if you take this exam after 2027 when they make the revisions. If n is 10 in each of these different cases, then this factor is 1/9 in each of the different cases. And since it's the exact same in each of the different cases, we can essentially just ignore it. Whichever case leaves us with the largest value from this red factor will have the greatest variance and therefore the greatest standard deviation. So what is this red factor? Well, as you may be aware, this symbol here is an uppercase sigma, and what it tells you is to add up a bunch of things. Those things are described in the expression just to the right of sigma. So in this case, we're going to add up a whole bunch of xi minus x bar squared. What is xi minus x bar? Well, x bar we've already seen. That's the sample mean of 5 here. And all xi is a symbol to represent each of the different observations. So all this is saying is take each of the different observations and subtract x bar. In other words, figure out how far an observation is from x bar, and then square that value. Add that up for each of the different observations, divide it by 9, and you have your variance. Oh, right, that's exactly what we did up here. When I talked about how much an observation would contribute to the standard deviation, we looked at how far the observation was from the mean, in other words, xi minus x bar. But then I said, be careful, it's not the distance that you care about, it's the square of that distance for this little 2 right here. So I guess to kind of summarize, what we really did is we looked at the 5 different cases and figured out which one would have the largest value of this expression in red. We then took advantage of the fact that there's the same number of observations in each case, so the factor in blue is the same. So whichever one has the largest value in red is going to have the largest variance. And then we took that one step further and said whichever one has the largest variance automatically has the largest standard deviation. So this problem, though, is probably done by most people in less than a minute, and is arguably the easiest problem on the test, is really a little bit deeper than you might think. I certainly don't want to kill your confidence. If you looked at this problem and were 80% sure that the answer was B, throw down B on your test and move on. But for the sake of making sure that you'll be that confident when you see a similar problem on your test, I wanted to go kind of deep into why this works. Yeah, it got a lot more confusing than the original question was, but hopefully that was worthwhile to build up your knowledge base so that when you see a similar problem, it feels easy to you on your test. I won't always go this deep into the problems, but hopefully it was time well spent for this specific video.